Our first speaker today will be Andrei Nita. He's Chief Technology Officer at McKinsey Intelligence Services. He will present a groundbreaking approach to detecting building damage using satellite imagery, advanced computer vision techniques. This talk highlights the integration of remote sensing with AI-enhanced disaster management, urban planning, and recovery efforts. Attendees, like yourself, will gain valuable insights in the real-world applications of these technologies. Thank you again.
Good morning, everybody. My name is Andrei, CTO at McKinsey Intelligence Services. I've been in engineering for the past 15 years, and I've specialized in data for the past 6 years, and AI for the past 3 or 4 years. My talk is building damage assessment or detection from imagery, satellite imagery and aerial imagery extensively. Who we are. The company was founded about 12 years ago by an ex-military imagery analyst that thought that they could bring military-grade intelligence to the commercial world. So they then tried to say, I want to cover the whole globe and map all major catastrophes, man-made and natural. These are the type of catastrophes that we cover. Agriculture, it could be like a crop not functioning anymore or not being fertile anymore. Drought, earthquake, explosion, fire. So you can see the full list over there. We have a team of intelligence analysts. They are NATO trained and they would have covered all major wars in the past. We like to say that they're so experienced that they could tell what type of tank, what year was built in from a satellite at 100 kilometers in the sky. So them kind of assessing building damage by hand is actually quite simple. Up until now, we've covered over 200 catastrophes all around the world. These are some of them, the ones for the past 3 months, at the time the photo was taken, which was probably a month ago. But up until now, yeah, we've covered 200 catastrophes. I believe that's about 30 or 40 in the image. I took Europe because the conference was in Belgrade, so I thought it was more relevant. But most of the events actually we cover are in the US. We have a lot of clients in insurance because, as you can imagine, this type of application is very important in the insurance industry because they can tell the situation on the ground within a few days of the event happening. We want to say that within 72 hours you'll have a pretty good idea of what the ground truth is like. We gather imagery, we gather all kinds of geospatial data, put it all in one big platform, and you get to see everything within, as I was mentioning, 72 hours. This I've just mentioned. I'm going to focus on hurricanes because our model is primarily trained and used for hurricanes. The kind of data that we leverage other than the imagery would be wind speeds, storm surge, flood depth. I'm going to go into what they are in the next slides. The type of assessments that we cover are not just at the building level, they're higher level, 5 by 5 kilometer grids, 1 by 1 kilometer grids, and building level, as I mentioned. All with their own damage ratings. And these are the 6 damage ratings that we cover. A lot of people, a lot of other companies in the field would generally give you 2, either no damage or damage, or 3, no damage, light damage, heavy damage. But we go up to 6. It makes it much more complicated, but also much more useful to our clients. These are just some of the previous hurricanes. The 3 major ones in the US, 1 per year, 2021, 2022, 2023. And I'll go through some of the columns. So as you can see, Ida, for example, in 2021 was the longest, 15 days. But Ian, for example, had 250 kilometers per hour, average wind speed, the highest IDA, 160. But I think the most important part that you will see is that it's not necessarily the surface area that matters, which is the last column, it's the buildings that are impacted, because the path of the hurricane might have passed through a very busy city. So there will be way more buildings impacted, a lot more claims being sent into insurance companies. But this sort of gives you an idea of the scale, how many buildings are impacted, how many buildings you would need to assess damage for, and what the model would have to kind of handle. Before we built the model, everything was done by hand by the intelligence analyst. They would look at every single house and give out a damage rating. So the classifier now has the difficulty, I would say, or the challenge of matching the human, the military-grade experts, because their accuracy is over 95%, because they look at every single house and assess the damage, and they also take a more holistic view to kind of assess that damage. One example that I can think of is two houses might look identical in terms of damage. You could say they're both light damage, but the pool of one of the houses has silt on the bottom and it's empty, which means there would have been a flood over there, but the water was blown away by the wind, but the silt was left over. So that means the foundation is, has had water damage, so probably there's a risk of internal damage for the building, right? That's not something anyone would ever know by just looking at an image with a pool with dirt inside. They would just think it's probably just mud that fell in. The computer vision model that we have is an ensemble one because it adds the imagery, but also building footprints to extract the actual perimeter around the building for the model only to receive an image with that building. As you can see, the red outline will extract only the building and not the grass or the trees or anything else around it. Over here, you can see on the left-hand side what an intelligence analyst would have estimated, and then on the right-hand side, yes, what the model would have estimated. The way we estimate the accuracy of the model is one damage class difference is okay. So as you can see, the model would have said substantial, but so the one on the top, for example, but the analyst would have said moderate. That's just one damage class above, but that's acceptable for us because it's very comparable. Remember, we have 6 damage ratings, so the difference between the damage rating is much smaller than, let's say, if you only had 2 or 3 damage ratings. We estimate that the average accuracy is about 80% for the model at this point, which is quite high. On the market, a lot of the other models would have around 60, 65. But again, it really depends on your input data, because you might have cloud cover over the imagery, which will affect the accuracy. You might have low resolution, myriad of other reasons. This is a screenshot from the platform itself, where you could see the wind speeds around Florida. I believe this was for Ian, and you could see the really high wind speeds that would have hit the coast of Florida. Some of the key factors that we will look at on the next slides that impact the damage rating would be wind speed, wind direction, storm surge, distance to coast elevation, infrastructure, and vegetation density. What is a storm surge? It's a change in the level of the sea. So generally, you now see those blue squares, but imagine that was not there because there wasn't any water there. This was just a Fort Myers beach, so a regular beach, but because of flooding, seawater would have come in and inundated all of those areas, also along the canals, for example, that you see over there on the top. And this can affect, of course, the foundation by adding water damage to the cement, for example, that the foundation was built on, or maybe it's wood. So it has a very high impact actually on damage. Elevation as well. This is a digital elevation model. The more red, the higher. Lower elevation will have more water because water will pool at the bottom, again affecting the foundation and potentially eroding that foundation. Dense vegetation as well. One big issue is that a tree might fall over your house and affect it, so your house might be fine, but because the wind was so strong, a tree might have fallen on it. Branches as well can cause quite significant damage. Distance to coastline is another really big one that was very impactful in our assessment because, again, you would be closer to the water, so you would have higher winds, you would have a higher storm surge, so the flooding alongside the higher wind speed will impact the assessment. Other than all of those methods we used to optimize the accuracy after the computer vision model, we also looked at the fact that damage tends to cluster, in the sense that if you have 10 houses and let's say 9 of them have no damage and one of the houses in the middle is destroyed, if that's what the model says, it's likely that that house is not destroyed and the model might have been wrong because the input data might have been to the side, let's say, so it maybe didn't capture the whole house, so the model assumed that the house was gone, maybe half the house was gone. So we added a nearest neighbor algorithm as well to kind of smooth the output because, again, damage tends to kind of be consistent across the different regions. The one on the left would be without the algorithm, the one on the right would be with the algorithm. Probably the points to note would be the red ones, I believe that's red, at the top, or purple. Those ones over there that have been smoothed to an orange or a yellow. And this is a diagram of the model, so what goes in. So you have imagery, satellite or aerial of different resolutions, building footprints, so those are the polygons that would tell you what the building looks like. With that, you then have a collection of images. Each image represents the building itself that you can then feed into the model. The model would have been trained with the exact same images, but from previous events and assessments that were done by hand by the military intelligence analysts. So you have the multi-class model, which is the first part of the computer vision model. We realized that you can't just have one single model for it, you need actually 3 different ones. So the first one separates undamaged buildings from some damage to completely destroyed. So then we keep the destroyed and we pass the other ones again. Then we have the binary model. It says undamaged and other damage type. So we keep the undamaged or no damage and the destroyed from the past to the side, and then everything else we pass again in the final multi-class model where we separate light, moderate, substantial, severe. Hopefully that made sense. But remember, we have the 6 ones, so we do 6 first, put it aside. We do 1 after, put it aside, and then the last 4, right? This is just the computer vision part. Then we add the optimizations like nearest neighbor, distance to coast, storm surge, etc. And what comes next afterwards? We want to cover more event types. We've mainly done hurricanes. We've done tornadoes as well because they're quite similar. Actually much simpler because a tornado has a clear path and you know the wind speed at every point with a lot of accuracy. So it's actually much simpler to do tornadoes. We want to cover more event types, wildfires, earthquakes. The issue with wildfire, for example, is that fire damage looks very different from wind damage. The buildings tend to be a lot darker because of smoke. So the model won't predict with the same accuracy. The same computer vision model won't predict with the same accuracy. Earthquakes, again, might be very different because they will change the shape of the house quite a lot, or they might sink the house. A lot of different changes that, again, the wind-based model wouldn't have been trained on. Improving the accuracy, we'll try to find new ways of improving that accuracy. And more ways to assess damage, maybe a separate computer vision model that can look at the presence of debris on the house or trees that might have fallen on the house, and etc. And if you want, you can follow us, sign up for the newsletter. That's us on LinkedIn, that's us on X. And that was it, that was my talk. And if you have any questions, please.
If you have any questions, just give it a second. Here you go.
Thank you for your presentation. Very interesting. I'm just curious about the frequency of getting satellite images you get. I mean, I have, you know, if you could just share how it looks more or less. I mean, it's like few images per day. What's happened when the clouds are when it's really cloudy? How it looks?
Yeah, great question. So we already have a base map, a global base map. There would be probably up to 3-4 years old in several regions. It might be like 1 year old in some regions. So the more popular the region, generally the more updated it would be. Similar to Google Maps, right? You can see when the last image was taken. That is the base map. That is like the before the event. After the event, we contact a lot of our suppliers and we ask for images generally every day. So let's say there was landfall today, then we'll have today, tomorrow, the day after, maybe another day after that. And we'll have different resolutions as well, maybe 50 centimeter satellite, 25 centimeter satellite, 15 centimeter satellite. And some customers might also want aerial, and then we can also get aerial all the way down to 7.5. So generally, to answer your question, daily, and it could be satellite and aerial. If there's cloud cover, we'll still get it because people still want to see. And then hopefully the next day will be less cloudy. Yeah, no problem.
Any more questions? Thank you, Andrei, very much.
Thank you, everybody.